Before describing Rutherford scattering, I first need to say a few words about what the cross-section is in scattering measurements. And it's the idea of a picture of something as taken in cross-section. So in a scattering experiment, we have a beam, usually, and a target. So the beam, pictured here by these particles going like this, is characterized by the number of particles per area per time. In other words, particles per centimeter squared per second, as I show here. The interaction of the beam with the target is characterized by how many interactions happen per second. So how many of these particles hit per second, or some amount of time, but seconds can be used. And then the most important thing to remember, and you should remember this for the rest of your life, what does the cross-section mean? It's the interaction rate divided by the flux. So if you look at the units of that, it's the interaction rate in inverse seconds, and the flux in per centimeter squared per second. The seconds cancel, and the centimeter comes up on the top, and you have something of units area. In this case, of this hard sphere scattering off the beam particles, the beam particles that hit it get scattered off, those interact, and what's left is this clear space, which is the cross-section at the area of your hard sphere. In nuclear and particle physics, we often use the unit of a barn, with a little b as its unit. So one barn is 10 to the minus 24th square centimeters, or in other words, a square area of 10 to the minus 12 centimeters by 10 to the minus 12 centimeters. So we should point out that you can't always measure the whole cross-section, and you often want to find the amount of interactions going off in a given direction. And for that, we have a differential cross-section. So, but if you measure the particles going off in some particular direction, an exact theta and exact phi, you don't get anything. So you need a little area here, or to put that in angular terms, a little unit of solid angle, d omega. So we want, and usually that's measured by some amount of phi times sine theta, as in the azimuthal direction, and d theta in the theta direction, and you get a solid angle. And then you split up the solid angle, or the cross section, into those parts. You get a differential cross section, d sigma d omega. How much of the cross section goes into the particular area? And now you can add all these up if you add it over all the solid angles to get back the cross section. So here's an actual picture of Rutherford scattering. It comes in, interacts, goes out. If you want the ones going off at some theta, integrate it over all the phis, then you have this shaded area as the solid angle, and you want to know how much goes there.